We now want to discuss some examples of Galois groups of cyclotomic polynomials. So let us first fix notation. So let us call u of n as set of positive integers less than n and relatively prime to n. So this is also denoted like this, z over nz with this sign here, which denotes basically positive integers less than n and relatively prime to n. So this u of n forms a group under multiplication modulo n. So for example, u of 10 is 1, 3, 7 and 9. So all the numbers which are relatively prime to 10. U of 5 is 1, 2, 3, 4. That is all the numbers relatively prime to 5. 5 is prime anyway. So in fact, for a prime p, your group is just 1, 2, 3 all the way to p minus 1. So this var phi of n is the Euler phi function, and the definition of var phi of n or phi of n is precisely the size of the group u of n. So that is the number of elements which are relatively prime to n. So now you can see var phi of 10, count the number of elements here, 1, 2, 3, 4. So there are 4 elements. And now you see var phi of 5 is 5 minus 1, 4 elements. So in general, you can see var phi of p, number of elements here would be p minus 1. So we already know this extension, you adjoin zeta n to rationals over rationals, is Galois. Now this is Galois precisely because this is a splitting field of a separable polynomial, which is our cyclotomic polynomial here. So Galois group of this cyclotomic polynomial will permute the primitive roots only, precisely because this cyclotomic polynomial was constructed out of primitive roots. So for example, all these are roots of this equation, x10 minus 1. So you can see there are 10 roots. Out of these, the primitive ones are precisely the ones whose powers are relatively prime to 10. So this we have seen before. So this is a primitive root, then 3, then this 7, and then this 9. So now you can see the correspondence, 1, 3, 7 and 9. So 1, 3, 7, 9, and 10 is 10 here. So the cyclotomic polynomial here is generated by these roots. So you take this here, 7 here and 9 here. So the Galois group will permute these roots only. So now we know that this we have shown before. So this we have shown before, that degree of extension of q of zeta n over rationals is our Euler phi function. And now we are saying that this is a Galois extension. So therefore the size of the Galois group is equal to this. So this thing is equal to this degree of extension, and this degree of extension is var phi of n. So the size of the Galois group is precisely var phi of n, and this comes from our cyclotomic polynomial being separable. So now this gives us a clue that the size of this group is var phi of n and size of this group is var phi of n. In fact, there is a one-to-one correspondence between our Galois group and u of n. So u of n and the Galois group, there is one-to-one correspondence. So you take a modulo n, you map it to element sigma a, and sigma a basically takes our first to sigma n of a. So this a gets mapped to this element here, the map which takes zeta n1 to zeta n a. So this is more clear from an example. So say you take u of 10 on this side, and correspondingly the Galois group will permute these elements. So the Galois group will consist of this. You have zeta 10 here, and the Galois group has all these maps. So it has these 4 maps, and the first map corresponds to one identity map. It takes zeta n to zeta n, so 10 to 10. The second map corresponds to our sigma 3, takes 1 to 3, so 3 goes to sigma 3. 7, you have this map sigma 7, this goes to here sigma 7, and for 9 we have this map, this goes to here sigma 9. So now you see the maps and one-to-one correspondence. So again, this is this, this is this, this is this, and this is this. So these two things are isomorphic. Now this is very advantageous because we already know a lot about un. So let us recall some properties of un which are generally covered in an elementary course on group theory. So u of 2 to the power of n is again a cyclic group, z by 2z times z over 2n minus 2z for n greater or equal to 2. For p odd prime, this u of p alpha is z over p minus 1 alpha minus 1 p minus 1 z. So these are formulas which are important to remember. You can find them in most textbooks on group theory. So say your n is given like this. It's a product of distinct primes. In each prime has a power a1, p1 is a1, p2 a2, and pr ar. So product of these primes with different powers, and pir distinct prime. Then u of n is this iso to up1 a1, up2 a2 all the way to upr ar. And generally once you have this composition, you use either this formula for power of 2, or for odd primes you use this formula to calculate u of n. So for example, u of 105 is, you decompose 105, so it is product of 3 times 5 times 7. So this will decompose as u3 times u5 times u7. Now all three of them are odd primes, so we are going to use this formula here. Alpha is 1, so this first term goes away. This term will go away for all three of them. So just set with z over p minus 1z. So corresponding to 3 you have 3 minus 1 z over 2z. Corresponding to 5 you have z over 4z. Corresponding to 7 you have z over 6z. The 7 minus 1 6, 5 minus 1 4. So we are using this formula here because the power of 3 is 1, power of 5 is 1, power of 7 is 1. So alpha minus 1 becomes 1 minus 1 0. So p to the power of 0 is 1. So this factor goes away. So now focus on this important isomorphism map. So this we carry it right here. So Galois of zeta n adjoint to rationals over rationals. So this is this, and un you're carrying here. So un will split like this. For this formula, we are carrying it right here. But now each of these groups is iso to the group above it. So this is iso to Galois group here, this is iso to Galois group here, this is iso to Galois group here, by this relationship. So now you can use this property to compute Galois groups like this. So say you are asked to compute this Galois group of 105 over rationals. So we immediately know that this is equal to our u of 105, which is equal to this map right here. So Galois group of this extension, your joint zeta 105 to rationals over rationals, is precisely this, times z by 4z. So cyclic group of order 2, then cyclic group of order 4, and then cyclic group of order 6. So this is one of the standard questions which are asked in examination, because you can put as many variations to this as you want.